Hello, welcome to lecture 11 of the course. In the last couple of lectures, we have learned about the density matrix formalism. In this lecture and the next, we are going to use this formalism to understand some basics of quantum computation. So, let us begin. We all must be aware that at the core of quantum computation is the so-called qubit, and we have already learned about it when we discussed two-level quantum systems. In this lecture, I will take you through certain concepts very quickly. Now, there are three key components of quantum computation. Firstly, there is the so-called qubit, which you are already aware of, and then we have to do the qubit manipulation, and qubit manipulation is done by the so-called quantum gates, and we are going to discuss about quantum gates in this lecture later on. And finally, for quantum computation to be effective, all these qubits must be entangled. Qubits must be entangled, and to address this fact, I am going to discuss briefly about the phenomena of quantum entanglement in the context of quantum computation. Alright, so before I go further, let us quickly revisit classical bits. You know, classical bits is basically the basic building block of classical information processing is bits, and bit, as you know, is a binary unit of information, and it stores only the values 0 and 1. Physically, if I talk about the physical realization of a bit, so it can be a bit may be a electricity, that means the current traveling through a circuit. Either it is traveling through a circuit, then we can say it to be 1, and if it is not traveling to the circuit, then we can say it to be 0, or say if the voltage is high, then we can say it's 1, and if the voltage is low, then we can say it to be 0. Okay, and similarly a bit may be, we can denote it by true or false, true for 1 and false for 0, or vice versa. Or a bit is can be also a switch that is turn on or turn off. Or even we can think in terms of a light bulb, which can be either on or off. So everything that is our computers, supercomputers, servers, calculators, etc., store information using classical bit. Now, in classical bit processing, every data can be represented as a binary. For example, this word bat can be converted to SCI code in numbers. We can write it as say 98, 97, 116, which can be converted back to the binary in this form. You can recall that I am sure all of you know how to convert a decimal number to a binary. For example, this number 108 can be converted to a binary by this process, as you can see here. And if it is converted to binary, this number 108, decimal number 108 in binary, I can write it in this particular form. Alright, and all types of files can be represented as binary, and the processor, classical processor, do the calculations and give the process output using these binary numbers. It can not only store text files but also image files, audio files, etc. All these can be converted to binary and stored in a computer. For example, if we consider an audio file, it is first converted to, by analog to digital converter. It is written in a digital format, and using digital signal processor, it is stored in memory in the form of bits, and then we can retrieve this information for this information that is stored in bits by again using digital signal processor, and then from digital to analog converter we can convert it back to a audio signal. I think these things are I'm doing very quickly because all of you must be aware of it and you know it. And now coming to the qubit, and we already know about what is a qubit. It is similar to bit, but it is a very distinct concept because qubits can be in a 1 or 0 states just like classical bit, but there is a catch here because there can be 0 and 1 state at the same time. Now here, rather than and or, you are writing and, right? So it can be at both 0 and 1 at the same time, and this property, as you know, is called the superposition principle of quantum mechanics, and it is the basis of qubit. And a quantum bit or qubit is a unit of information describing two-dimensional quantum system, which already we discussed when we have discussed about two-level quantum system in an earlier lecture. Now you can differentiate qubit from bit by this exchange of notation. 0, this bit you can convert into a qubit. 0 is written as kth0 and 1 is written as kth1. So here this kth0 and kth1, as you know, are the two possible states of the qubit, and as you know that qubit can be both in 0 and 1 at the same time, so mathematically it is can be represented as a superposition of kth0 and kth1. And in fact, a classical bit, as you see, it can be either in 0 or it is in 1, but a quantum bit can be both in 0 and 1, so it is going to be in this particular sphere at any place of the sphere at the same time, right? It's covering this rather than having two separate sphere to represent 0 and 1. You have a one single sphere to represent both 0 and 1, and this is the so-called Bloch sphere, as we have discussed. I think I'll make some further comments later on. Now coming to these qubits, if we have this number of qubits, suppose we have just one qubit, the corresponding or the equivalent number of classical bits are going to be 2, because 0 and 1. And if we have 2 qubits, so that means that classical bits is going to be 4. Okay, so similarly, if we have 3 qubits, then number of classical bits are going to be 8, and if we have n number of qubits, then the classical number of bits is going to be 2 to the power n. So therefore, if there are n qubits, there is 2 to the power n number of possible states. That means it can be in all the states at the same time, and also here qubits will also have equivalent number of bits as that of classical bit, one at a time. But the advantage here is that it can use all the bits at the same time, and this is why quantum computation is so powerful over that of the classical computation. Okay, now you know a classical bit can do only single calculation at a given period of time, whereas qubit can exist simultaneously in multiple states. So therefore the so-called quantum parallelism is possible. So it is the greatest advantage of quantum computation, because it is possible to do parallel processing of the tasks. And now, as we have discussed earlier, we can use spin as a qubit. That means, for example, an electron, if you consider, it may be in the either spin up state or the down state. Spin up state can be represented by this up ket state, and the down is represented by this down ket state. So this up state, as I have commented earlier, up state can be represented as kth0, and down state can be represented by kth1, and corresponding matrix form would be this column vector for up state, or kth0 would be 1 0 and kth1 is going to be 0 1. So it is basically a choice of convention. You can use kth0 as 0 1 or kth1 as 1 0. But if you stick to one particular notation, you should be stick to that throughout your calculations, right? So for example, here we are considering kth0 as 1 0 and kth1 as 0 1. Now any arbitrary state of the qubit can be represented as a superposition of kth0 and kth1, and we already discussed all these things in an earlier class. So because of this, we can represent the arbitrary state of a qubit by this column vector, and we just need two variables theta and phi, and this basically leads us to the so-called Bloch sphere, which we have discussed in great detail. It basically means that any qubit state can be represented by a point. Every point on the Bloch sphere represents a quantum state, and here you see this north pole of this Bloch sphere represents kth0 and the south pole represents kth1, and we have various kinds of states possible. Any arbitrary state, for example, this particular point, say P, it's represented as a superposition of K0 and K1, and depending on the value of theta and phi, I can have various qubit states. For example, for theta is equal to 0, phi is equal to 0, I have K0. For theta is equal to pi and phi is equal to 0, I have K1, and so on. And for another important is this state is the superposition of equal superposition of K0 and K1, that corresponds to theta is equal to pi by 2 and phi is equal to 0. For example, this particular point M here in this picture here, that represents the equal superposition of K0 and K1. This is also known as one of the diagonal state. And at the equatorial plane of the Bloch sphere, I think all these things we have discussed earlier. I'm just rushing through all these things. So we have, for example, this one, when we have theta is equal to pi by 2, phi is equal to 0, we have equal superposition of K0 and K1, that represents that is the so-called, say, K plus. And for phi is equal to pi, we have again equal superposition of K0 and K1, but with a inverted sign here before K1, that is minus sign is there. This is represents the K minus, and these are called the diagonal basis. K plus and K minus form the diagonal basis. On the other hand, K0 and K1 are the so-called computational basis. And the advantage of this diagonal basis, these things I think you can easily make it out. We discuss all these points on the Bloch sphere here. Now, utility of the diagonal basis is that we can actually get the information about the phase between this state K0 and K1 if we work in the diagonal basis. If we make measurement in the diagonal basis, that gives us the information about the phase between the two states, that means K0 and K1. If we work in the computational basis, then we are going to lose the information about the phase between the two qubits, that means two states K0 and K1. Now let us quickly discuss about the two-qubit system, which is basically a composite system, and we have discussed about composite system in the last class. If I consider about two classical bits, say we have set of two bits 0, 1 and 0, 1, 0, 1, then it's going to form this composite set. There is going to be 0, 0, 0, 1, 1, 0, 1, 1. You can either have 0, 0, 0, 1 or 1, 0, 1, 1 at different times. But if we consider the corresponding quantum 2 bits or 2 qubit system, then all of them can remain at the same time. It would be basically going to be a superposition of K00, K01, K10 and K11. And this superposition is constructed in such a way that all these coefficients, as you can see from here, it's going to be satisfy these conditions. That means this basically means that this quantum state representing this two qubit system is normalized. And here the convention is that in this kind of system, if I talk about the first one, say K00, the first K represents the first qubit and the second one represents the second qubit, as we have commented that in the last class as well. And similarly, say K10 is the first one, K1 corresponds to first qubit, K0 corresponds to the second qubit, and so on. And now you see, if we make a measurement on this two qubit system, and if you want to get 0 as a measurement in the first qubit, then if you look at this quantum state, then you will see that this K0 in the first qubit is belonging to this term here and this term here. So associated coefficients are alpha 00 and alpha 01. So the probability of measuring 0 in the first qubit is would be basically the sum of alpha 00 mod square plus alpha 01 mod square. And after making the measurement of the first qubit, the post measurement quantum state is going to be simply this. Okay. Now let me talk about manipulation of quantum bits or qubits. Qubits are manipulated by the so-called quantum gates. Quantum gate operation takes a qubit from one point on the Bloch sphere to another point on the Bloch sphere, and quantum gates are analogous to the classical logic gates. For example, all of you know about the classical NOT gate, and you may recall that the symbol for the classical NOT gate is this, where say X is the input and Y is the output. What it does basically a NOT gate, a classical NOT gate converts a bit 0, it transforms a bit 0 to bit 1 or bit 1 to bit 0 at the output. And we know about this table here, input output table. If x is the input, if input is 0, then because of the NOT operation, output would be 1, and if input is 1, then the output would become 0. Alright, now in the quantum context, we have, instead of bit, we have quantum these gate states, say gate 1 and gate 0, and we want analogous gate operation there in quantum regime, where say we have this gate 1, then because of this NOT operation, quantum NOT operation, we should get at the output gate 0, and if the input quantum state is gate 0, and then at the output the quantum state should be gate 1. Alright, so basically this is done by the so-called Pauli matrix sigma x. Sigma x does that. In fact, you know that sigma x is the Pauli x component of the Pauli vector, or sigma x is the Pauli operator, x component of the Pauli operator, and in matrix form it is represented as 0 1 1 0, and you can easily check that indeed if Pauli operator is applied on the gate state gate 1, then it's going to convert it to gate 0. Let me quickly show you, because you know that sigma x, that's the Pauli operator, x component of the Pauli operator, so this would be represented in the matrix form of 0 1 1 0, and gate 1 is represented by the column vector 0 1, and if you do the matrix multiplication, you will see you are going to get here simply this would be 1 and this is going to be 0, and you know that this is nothing but your gate 0, and this guy is your gate 1, and this is your sigma x. So you see you are basically inverting gate 1 to gate 0, and similarly you can do if you operate on the gate 0, it's going to give you gate 1. So therefore this Pauli matrix, or this Pauli operator sigma x, x component of the Pauli operator, x like a quantum NOT gate, it basically exactly do the same thing as that is done by the classical NOT gate. And in general, rather than using this sigma x as the symbol for NOT operation, quantum NOT operation, the symbol x is used. So for example, if this x, which is nothing but sigma x actually, if it operates on a superposition of the quantum states, say a0 gate 0 plus a1 gate 1, then because of this NOT operation, the resultant state would become a0 gate 0 is going to convert it to gate 1, and gate 1 is going to be converted to gate 0. Okay, so this is what the action of the NOT operation. Now let me talk about another important single gate operation, that is called the Hadamard gate operation. So in the Hadamard gate operation, it is represented by the symbol H. Don't get confused with the Hamiltonian, it's just Hadamard gate, and it is defined as follows. When the Hadamard gate operation is done, if it operates on the quantum state gate 0, it converts it to a superposition state, equal superposition state 1 by root 2 gate 0 plus gate 1, and in fact if you recall, this state is nothing but your diagonal state gate plus, and if the Hadamard gate operator operates on the quantum state gate 1, it converts it to 1 by root 2 gate 0 minus gate 1, again equal superposition of gate 0 and gate 1, but with a minus sign here before gate 1, and this is nothing but the another diagonal state gate minus. And in fact, what you see is basically this Hadamard gate operation. If I think in terms of the Bloch sphere, you have this Bloch sphere, and suppose before Hadamard gate operation your quantum state is in the south pole, which is your gate 0. Now because of the Hadamard gate operation, so let's say this is my x-axis, this is my y-axis, this is my z, this is my north pole, this is my south pole, right? This is gate 1, and this particular point is, as you this is in the equatorial plane, right? In fact I am talking about this point. Say this is point M, and this is the point at the equator, and this point corresponds to, if you recall from your Bloch sphere this discussion, this point M represents the quantum state 1 by root 2 gate 0 plus gate 1. So if you see that, if you can see it, that what Hadamard gate operation is basically doing, when it is operating on gate 0, it is taking the quantum state from the point S to the point M, right? It is because at the point M the quantum state is 1 by root 2 gate 0 plus gate 1. So this is what I mean by qubit operation. That's how gates are used to do qubit operations like this. So when I said that qubit operation or quantum gate operation basically take your qubit state from one point on the Bloch sphere to another point of the Bloch sphere. For example, in this case, the quantum state is taken from the point S to the point M on the Bloch sphere. So I hope you get the idea. Now in the matrix form, this Hadamard gate operator, Hadamard gate can be represented by H, or sometimes it is also given by the symbol UH, because ultimately this gate operations has to be unitary operation. In the matrix form, it would be written as 1 by root 2 1 1 1 minus 1. I urge you to please verify it, otherwise we will do it in the problem solving session. Now let me talk about a very useful and important 2-qubit gate. So far the Hadamard gate and the quantum NOT gate that we are discussing are single qubit gates. Now let us consider about a 2-qubit gate, and in this context let me talk about the most important and most useful quantum 2-qubit gate is the so-called C0 gate, and it is symbolically represented as follows. So you have here the first qubit, and the second line represents the second qubit, and this is how it is symbolically, this is how it is represented. This is the C0 operation, C0 gate representation. Here the first qubit with this dot here, this represents the control qubit, and this one, or the control bit, and the second qubit represents the target. Okay, I'll explain what it means. In fact, okay, let me tell you that this one line represents the first qubit, and this second line refers to the second qubit. And here the rule of the game is as follows. The rule of the C0 operation is as follows. If the control gate is a say gate 0, if control is gate 0, then the target remains as it is. Then the target bit, whatever it is, target bit remain as it is. Target qubit remain as it is. Okay, it does not change. If the control, on the other hand, if the control is say gate 1, then the target gets target qubit, then the target qubit qubit gets flipped. Okay, so let me explain it further. Here it's actually qubit. Okay, what I mean by this is this: say you have at the first qubit you are putting 0, and in the second qubit, second line, you are putting 0. So this first qubit refers to your control and the second one represents the target. Now as you see, because of this C0 operation, if the control is 0, then target is going to remain as it is, so you are going to get at the output simply 0 0. On the other hand, again, suppose you are having 0 at the control and 1 as the target, because of the C0 operation, you are going to get it at 0 and 1 because the target qubit is not going to get flipped. But if your target control is 1 and the target is 0, because of the C0 operation, you see that your input is going to remain as it is, but the target control is remain 1, but the target is now going to get flipped and it will become 1. And if the control is 1 and the target is 1, then because of the C0 operation, as per the rule, it would become 1 0. Now you see the target qubit is getting flipped. So what is happening is, so let me summarize its operation. When C0 gate operates on gate 0 0, it would become simply, it will remain as it is. If it operates on say 0 1, it would again remain as it is because your control here is 0. And if it operates, C0 get operates on 1 0, because your control is now 1, so target is going to get flipped, so it would become 1 1. And if it operates on 1 1, then the target is going to get flipped and it would become 0. Now this helps us to write the matrix representation of the C0 gate, and the matrix representation of the C0 gate is as follows, and I think you can easily make it out. And it would be 1 0 0 0 0 1 0 0 0 0 0 1 0 0 1 0. I urge you to find it yourself that it, yes, indeed this is the matrix representation of the C0 gate. Now you see there are various combinations of gate possible, and these various combinations of gates forms the so-called quantum circuit. Let me give you some example. So various combination gives us quantum circuits. For example, let's say we have this Hadamard gate operation in the first qubit, and this Hadamard gate is followed by a C0 gate like this. So this is a quantum circuit. So here you are having two gates. One is this Hadamard gate and another one is the C0 gate. So it's basically a combination of two quantum gates and it forms a quantum circuit. And this quantum circuit is very useful, and let me give you an example. Suppose you put at the input you put gate 0 in the first qubit, and in the second qubit you put gate 0. So what it is going to do, first Hadamard gate operation let us discuss. If the Hadamard gate operation is applied, it is going to act on the first qubit only, because Hadamard gate is a single qubit operation. So what it's going to do, it's going to convert this gate 0 to 1 by root 2 gate 0 plus gate 1, and the second qubit is going to remain as it is, and this is going to simply give you you will get gate 0 0 plus gate 1 0, and now this guy, this output is going to act as an input for C0 gate, right? Because the Hadamard gate is now followed by C0 gate. So C0 gate is now going to operate on this particular input 1 by root 2 gate 0 0 plus gate 1 0. Now you see, because of the rule of the C0 gate operation, if you look at the first term, because the control gate is 0, control qubit is 0, so target is not going to get flipped, so you will have gate 0 0 only. But in the second case, you will see because the control is 1, the target is going to get flipped and it would become 1. So this is the state you are going to get, and this particular state is going to be the output at the quantum circuit, and this is an entangled state. So this particular state is an entangled state. It is one of the Bell state. So now let me discuss about quantum entanglement in brief. A quantum system is said to be entangled if its quantum state cannot be factored as a product state of its local constituents. Let us consider an example. Let us say we have two qubits A and B, and qubit A is represented by the quantum state, say kth psi A. It's a superposition of kth 0 and kth 1. It's a qubit. And the another qubit system B, its quantum state, arbitrary quantum state, is represented as a superposition of kth 0 and kth 1. Of course, these coefficients are now different for the system A and system B. They may be different from each other. Now, if you form the direct product of these states, then you will get psi A direct product or the tensor product psi B. In the matrix form, I can write kth psi A as A0, A1, direct product with the matrix form of the states kth psi B, that is going to be B0, B1. So this is going to give you the direct product of the two qubits in the matrix form. The would be I will just get A0, B0, A0, B1, A1, B0, and A1, B1. So this is called a product state. So let me give it an equation number. So this is a product state. This is a product state. Okay, in fact, in the state vector notation, this product state can be written as, let me write it in the compact notation, it's psi AB, and which is the direct product of psi A and psi B. And if I fully write it, then I will get A0, B0, kth 00 plus A0, B1, kth 01 plus A1, B0, kth 10 and A1, B1, kth 11. Right? Okay, let's say this is my equation number 2. And in fact, I can write it in a more compact form. If I write A0, B0 to be alpha and kth 00, let me write it as 1, kth 01 as 1, 2, or okay, let me write it a little bit differently. Let me say kth 00, this let me denote it by 0, and this one let me denote it by 1, and kth 10 let me denote it by 2, and kth 11 let me denote it by 3. And on the other hand, these coefficients A0, B0 let me denote it by alpha, A0, B1 let me denote it by beta, and A1, B0 let me denote by gamma, and A1, B1 let me denote it by delta. Then this composite system, this product state psi AB, I can write it as a superposition of 0, 1, 2 and 3, right? So this is an example of a product state. Now if you look at this particular state, and from this equation number 3 and equation number 2, if you look at carefully, you will see that this particular product state satisfy this property, alpha delta is equal to beta gamma. This property is satisfied, and we say because of this reason, because this property is satisfied, we are able to write it as a product state. In fact, you can please verify this condition, and it's very easy to see. If you look at the product of alpha delta, you will get A0, B0, A1, B1. On the other hand, beta gamma is product of beta gamma is going to give you A0, B1, A1 B0. As you can see, left hand side is equal to right hand side, so this particular property is satisfied here. However, not all states obey this particular property. This means that all composite states cannot be expressed as a product state. That means when we cannot express a composite system as a product state, such states are called entangled state. Product state, such a state is called entangled state. Let me give you some more examples. Entangled state. So for example, consider this particular state. Say ket phi is equal to 1 by root 2 ket 00 plus ket 11. In no way you can write it as a product state. And this state, that means what I mean by you cannot write it as a product state, that means you cannot write it as a direct product of, say, system A state and the system B state. Okay, you cannot write it this way, so therefore this is an entangled state. Now if you consider, on the other hand, if you consider this particular state, say ket eta is equal to 1 by root 2 ket 00 plus 01. Now if you look at it carefully, then you see that you can write it actually in this form: ket 0 direct product 1 by root 2 ket 0 plus ket 1. So this is clearly it's a product state, because this, say I name it as a psi A, so this is referring to system A, and this may refer to system B. So I can write it as a product state. Now there are a set of very important entangled quantum states known as Bell states, and these are very important for quantum information science and in quantum computation. These are as follows, and they are worth to remember. Let me just mention them. There are 4 Bell states. They goes as follows. Say phi plus is equal to 1 by root 2 ket 00 plus ket 11, and then you have phi minus, that's also a Bell state, 1 by root 2 ket 00 minus ket 11, and then you have psi plus is equal to 1 by root 2 ket 01 plus ket 10, and you have psi minus is equal to 1 by root 2 ket 01 minus ket 10. Now physical significance of these states, you just pick up any one of this system. For example, if I talk about, say, ket psi plus, this is one of the Bell state. Now you see it's a superposition of ket 01 and ket 10. What it basically means, it means that suppose you have this system A and system B, these two systems you cannot write, their states you cannot now write it as a product state, they are now entangled. What it means, if you make a measurement and if you find that this particular system is in ket 0, then automatically, even if you don't make a measurement, it basically means that the system B is in ket 1. Or if you find that the system A, because of the measurement, it collapsed to the state 1, automatically the system B is going to get collapsed to ket 0 if they are represented by, in that case they would be represented by this entangled state psi plus. Or if, say, if you make a measurement and if you find that system A is in ket 0, and because of the measurement you find it in A0, automatically because of the measurement the system B is going to be found in ket 0. Or if you find that because of the measurement system A is found to be in ket 1, then the system B is also going to be found in ket 1. And this is the situation that is expressed by this particular state. Say we have this one, right, phi plus, or even that matter phi minus also represent the same thing. It would be 1 by root 2 ket 00 plus ket 11. Okay, so these are called entangled state. Okay, this is what the meaning of psi plus, phi plus, and similarly for psi minus, phi minus. And if you look at phi plus and phi minus, they are basically different from one another by this by difference of phase here. For example, phi plus you are having plus sign here, and in phi minus you are having minus. Similarly for psi plus and psi minus. Let me stop here for today. In this lecture, we learned about some basics of quantum computation. We will continue our discussion in the next lecture. See you in the next lecture. Thank you so much.